This is a presentation of the Mouse Pacemaker project by Cody Clarksean, Colten Ferris, Christy King, and Tao Yang for NDSU Senior Design 2. Our advisor for this project was Dr. Ewert. Roles for this project: Cody Clarksean was in charge of the microprocessor, Colten Ferris was in charge of our leads, Christy King, myself, was in charge of the pacing, and Tao Yang was in charge of sensing. So, the purpose of this project is to build a mouse pacemaker. It's going to be used to pace the heart of a small animal. We are aiming for a mouse, but it could be any small rodent, really. We plan to be building an AVO pacemaker. This means it's going to pace the atrium of the heart and sense in the ventricle. So how does the heart pace? The SA node begins the heartbeat and then creates the action potential. It travels to the AV node. The AV node then delays the signal before it passes through the bundles of His, which contracts the ventricles. Essentially what you have is a polarization traveling from around the outsides of the heart and then into the inside, causing it to contract and expand. This project is a continuation of a senior design project from last year, so I'm going to tell you a little bit about their project. They designed an AOO pacemaker. This means that they paced the atrium of the heart, but they didn't do any sensing. They also used unipolar leads, and they were able to perform an impedance test and test their design on a mouse heart. They did run into some issues with their testing, though. They were unable to tell if the heart muscles were contracting or if it was just the skeletal muscles. You could see the heart moving in and out like a heartbeat, but they weren't actually able to tell if the blood was moving through the heart. That is one of the things we're going to be working on this year is capture detection. Sensing essentially is making sure that the blood is actually moving through the heart. They weren't able to meet their size requirements or the PCB layout due to the size of the components. This is a capture detection decision matrix. We had two ideas for capture detection. The first one was to use a photosensor and an LED. Basically what you would do is put the photosensor underneath the heart and the LED, a red infrared LED, on the top. The light would shine through. The photoresistor would measure the amount of light shining through, and as the volume of blood in the heart changes with the pulse, you would be able to read that in the photosensor, and that would let you know that the blood was actually moving through. We did dismiss that idea because it would be a device that would have to actually wrap around the heart. And as you can imagine, a mouse's heart is very small, about the size of your fingertip. So it really would be a difficult thing to work with while testing in order to work around it, make sure we're still applying the leads to the right places, as well as implanting it would be highly impractical. So what we're going to be doing now is sensing with VEGM. So the decision matrix goes over the different variables or factors of each type, and it calculates the total, which one would be more beneficial. And as you can see here, the infrared option lost. So the requirements we came up with for our project are to improve upon the previous group system and make their old system operational. This is basically to have a place to start to get going. We also want to re-examine impedance for a unipolar or bipolar system, create a decision matrix for the capture detection options, which you actually just saw on the previous slide, decide on unipolar versus bipolar system, research electrode material options, research pace signals, what's used and why. And then we also had a target size was listed here. We wanted to meet our budget restrictions, of course, And then we did aim to have a breadboarded circuit ready for May and a device that would ideally be implantable at the project's end, which would be in December this year. So looking at unipolar versus bipolar leads. The previous group used unipolar leads, which are more likely to sense the skeletal muscle signals. Basically what a unipolar lead is, it's one wire that connects to the heart, and the pulse and sense both go through that one wire. Or like the wave and the reflection both go through that wire. Bipolar leads are two leads, as you would imagine, to go to the heart. They're a lot less prone to interference, and since the sensing of the heartbeat was an issue for last year, we decided to go with the bipolar leads. We do have to be a lot more careful with impedance when it comes to bipolar leads, considering crosstalk and the variable. There's just so many more variables included, such as the distance the leads are apart and whether or not they're twisted, and many other considerations. Now, the electrode tip on the lead, we have a few options for that. We were researching materials that were commonly used, and we found that titanium, platinum, iridium, silver, and silver chloride are what's generally used. The titanium and its alloys are extremely biocompatible. They're resistant to corrosion, but they're pretty expensive. They're typically something that's used in industry along with platinum, and they would really be a great option, but given the budget that we have, it just wasn't viable for us. Likewise, the platinum is very good. It has a very low scar tissue buildup. When you apply the lead to the heart, you're essentially poking something into the heart, and scar tissue is going to form up, causing a higher resistance. It also has a high biocompatibility, high conductive, but it is not as biocompatible as titanium. Still pretty darn good. The iridium also has a high biocompatibility. It's better for small electrodes, and it's a better simulator. But overall, we're going to use the silver and silver chloride electrodes. They're not very commonly used in industry, but they are great at blocking bacteria from entering the human body, and they're within our price range. So when we're picking an electrode, we want to consider a couple of different things. First of all, we know that we want a small tip for the electrode. This will increase the density of the electrical field, and we want a large surface area to minimize our energy loss. Then the two questions we really have to ask about the materials are the biocompatibility and the biostability. So biocompatibility means, is the material safe to implement, such as will it cause the person to be sick or have an allergic reaction, etc., etc. As for biostability, it's going to be, will the body attack the material? Will you reject the leads? Will your body start attacking the leads and causing a massive buildup of scar tissue and other things around the leads, making them ineffective? That's basically what we're looking at here. So as I mentioned, we did choose silver chloride leads. We got them from AM Systems. They're going to be placed on the right atrium and the right ventricle, and we measured the impedance with the DC voltage, and it came to 0.22 ohms for each lead. Now we're considering the impedance of our pacemaker. We're influenced by a couple of things here. We have to consider the lead conductor, the electrode resistance, and the polarization. As you can see, we have an equation here. Z stands for impedance. Z total equals ZC plus ZE plus ZT. So essentially what that equation means is that to find an ideal lead, we would want a low conductive resistance, which would be our ZC, and we want a high electrode resistance, which would be our ZE. This will allow us to minimize our current flow and maximize the battery life. Now I'm going to explain what what effect polarization has. Alright, your current is flowing from the lead and electrode into the heart tissue. The current is basically electrons and negative charges flowing out. Having negative charges flowing out here is going to attract positive charges all around it. So we're going to have this buildup of positive charges right next to the electrode. And these positive charges, consequently, are going to attract negative charges. So if we simplify it, it's going to look like a capacitor. We'll have negative charges, and positive charges in the middle. This is going to impede our current flow as well. So we considered how to do an impedance test. Basically, this test would not be done on the mouse. It would be done in lab, using some sort of simulation for a heart. Eventually, it would be done on an actual mouse as well. First, we would want to run it on some sort of simulation of a heart in order to preserve resources. So we're going to have our function generator outputting some sort of signal, and we're going to have an oscilloscope on that lead, reading what our frequency, voltage, current, and all those kind of things are. Then we're also going to have a lead coming from the heart, which is going to tell us what our sensing signal is going to look like, what the signal from the heart is going to look like. So how are we going to pace the heart? There are two main options these days. There's a constant voltage generator or a constant current generator. The constant voltage generator is typically used for permanent pacemakers, and this allows the generator to output a narrower pulse. That's going to be particularly helpful for us when we are trying to generate the heartbeat of a mouse, which is about 700 beats per minute. The constant current generators are typically used for temporary pacemakers. The voltage will have to rise in order to remain and maintain a constant current. This is due to the polarization impedance increasing as time goes on. As I explained before, there's the scarring tissue and the charges building up around the lead. So here is an idea for the pacing circuitry. We have our pick going into 2 switches and a single inverter, and then we have our leads to the heart. So from the pick, we're going to be outputting a square wave. When the output is high, the pacing switch will be closed, and the bipolar leads will go to the heart, sending the pulse. This will go, the high will also go through the single inverter, which will make this low, essentially, and that will make this switch open. We'll have the sensing circuitry and the lead applying to the heart. When the pick outputs a low voltage, the pace is going to be open, so nothing is being applied to the heart. The single inverter is going to make this high, so the switch will be closed, and we'll be able to use our sensing circuitry in order to read the signal we're getting from the heart. So this is going to be a pretty quick switching here. It'll be pace, sense, in that kind of terms. So the pick we used this year was a bit different from the one they used last year. We used a 12F675. We picked this one because it has A to D capabilities. It has 4 times the flash memory as the one before. It has more input-output pins that are available to us. It uses less power, and the downfall of it is that it's slightly bigger in size. Here is a flowchart for our code, as it is right now. We're going to be initializing our microcontroller. This will turn on our analog to digital converter. We're going to pace the atrium of the heart and wait for depolarization to occur. That's waiting for the pulse to occur. We will then set sensing in the ventricle, and then if the pace is sensed, we're going to turn the indicator off, but if the pace is not sensed, we're going to turn the indicator on, and then we'll be waiting for the next pace to occur, and we'll set it to the pace and continue on like that. Now, what do I mean by indicator? This is basically a failure of detection, letting us know if we actually are detecting a heartbeat or not. Basically, is our sensing circuitry working? So the current design that we have right now is an LED that's going to light up when we are not sensing, and if it does capture a pulse, it's going to turn off. This will be controlled by a simple BJT switch into the PIC. In the future, we could possibly use Bluetooth, since the device is going to be implanted in the mouse. We won't actually be able to tell when the light is on or off. So having a Bluetooth transmitter could be incredibly beneficial with knowing whether or not it is actually working. Bluetooth is a lot lower power as well, but in order to make this design work, we would probably need a larger PIC. Those are all long-term goals, though, of course. Unfortunately, we are not as far in this project as we would like to be. We didn't allow for enough time to complete the necessary paperwork for the animal testing. And this semester was very much so research-based for us. I myself, prior to this project, had no experience with pacemakers or the anatomy of the heart, so it's definitely been quite the learning curve there. Another issue we had was we had too vague of a timeline with the Gantt chart. So here's the Gantt chart we had made at the beginning of the year. As you can see on the left-hand side, we really did block out everything we needed to do for the project, but we really didn't put it in specific enough terms. For instance, we have pacing circuitry right by my name here, and that is just so vague. It doesn't really break it down enough to be a reasonable estimation of a timeline. So we ended up making a more detailed timeline, and this is what it looks like right now. We have our impedance test. It's designed, it's written. We're still looking for an approval on it before we can run it. We've done a DC impedance measure on our leads. The code is in version 2.1. It's completed and in testing. We are also having some issues uploading it to the PIC. The pacing circuitry is designed, but I'm waiting on specific values before I can actually finalize it. Tao is testing his sensing algorithm, and we're all still working on our electrical engineering wiki page for the group. And here we're going to be going over the budget that we got. We were awarded a budget of $175. This is a breakdown of what we've spent so far. It's for our switches, our LED, our PIC, and the bipolar leads, which, as you can see, were our most expensive item, costing us $35.50. So we are currently at a budget for $118.41. Listed here are our rough estimates of what we're going to be needing to buy next semester. And it is a rough estimate, but if all goes as planned, we'll have about $8.11 to work with. So next semester, first and foremost, we're going to be getting our animal testing paperwork in order. We're going to start that right away, week 1. We're actually going to probably start it sometime during the summer here. And we're going to be waiting for the approval of that. And then we'll be doing the heart impedance test upon that approval. Week 4 is an estimate. We're hoping it'll be sooner than that, but you never know. Then we plan to finish our circuitry and coding in week 6, order a PCB by week 8, and allowing some time for the PCB to be made and delivered. We will then hopefully be testing on a mouse by week 12. So in summary, we're not as far as we expected to be this semester, and we are in quite a good position for next semester. We've done a lot of research, we kind of know where we're going from here, and basically it's having the time and the drive to sit down and really dig into it. If you have any questions, I would be pleased to try and answer them. You can leave a comment or send me a message, and I will do my best to get back to you. Thank you.